All right, let's begin. Hope you are all doing well. It's just a couple more weeks left, and that's it. Okay, so we are in chapter 8. We are learning hypothesis testing. Okay, and on Monday I gave a little bit of an overview of the ideas behind hypothesis testing, and we said essentially we start off with a claim and then we compare the reality versus the expectation. Okay, and if they are quite different, then perhaps the assumptions on which we made our expectations are wrong, and if they are quite similar, then the assumptions that we made for our expectations could be correct. All right, and so our textbook breaks hypothesis testing down into 4 steps, and so I'll kind of list them off here, and then we'll work through. We'll work through it. Okay, so step 1 is write your hypotheses. Okay, and so you have the null hypothesis, and then you have the alternative. Okay, and then the null hypothesis will always have an equal sign. And then the alternative will be identical except for the equal sign. Okay, so we say that the alternative is just has the equal sign replaced with something else. Okay, so that's the first step. You read through the problem and you try to figure out what your hypotheses should be. Okay, and the second step in our textbook calls this prepare. All right, and effectively this comes down to check the conditions to use the central limit theorem. Because ultimately our hypothesis testing depends on the use of the central limit theorem, and there are conditions that must be met in order for us to use that. Okay. Now, so in reality, step 2 is a very important step. To check the conditions for the central limit theorem is very important. Okay, but as far as writing tests and quizzes go, I feel like I'm writing these sneaky traps. If I set up a problem and I say, find the p-value and make a conclusion, but it was a trick because you were supposed to check the conditions and now you can't do the problem. Okay, so I'm not going to do that on the tests. Okay, so as far as checking conditions go, I have separate questions for checking the conditions, which you saw on the midterm. Okay, where you had to check the conditions, and then as far as tests, the problems where I ask you to solve for a p-value or make a conclusion, the conditions will be met for those problems. Okay, so that way I don't feel like I'm being too sneaky or something there. But it is an important step that we should check the conditions to use the central limit theorem. And basically, if these conditions are not met, you can't carry out the hypothesis testing, at least the way we've taught. Okay, you'd have to learn more statistics and use a different type of test. But So that's step 2. And then also part of step 2 is identifying or selecting your significance level. Okay, and that's alpha. Okay, significance level alpha. And if alpha is not specified, use alpha equal to 0.05. Okay, so if alpha is not specified in the problem or you can't figure out what alpha to use, just assume that alpha is 5%. And that's just kind of a default value that's kind of become the norm over time. Step 3 will be our calculations. And this can be further broken down into kind of like 3 sub-steps. So I'll call this 3A, which will be find the standard error. Okay. Step 3B will be get your test statistic. And as far as chapter 8 goes, our test statistic will be Z, or we'll just say test statistic is kind of the difference between our observed, the reality, the observed value, minus the expected value. So we're comparing the reality versus the expectation, but then we divide that difference by the standard error. Okay, so the observed minus the expected divided by the standard error. So this kind of gives us an idea of reality versus expectation. Okay, and then the last step, 3C, in this part will be use the test statistic. I'm going to just abbreviate TS to get a p-value. Okay, and I'll elaborate all of these steps in further detail. Okay. And lastly, after you get your p-value, make a conclusion. That's the last step. Okay, and the conclusions effectively are: if the p-value is greater than alpha, do not reject the null hypothesis. All right, and if the p-value is less than alpha, reject the null hypothesis. Okay, so let's try out an example problem. Just want to make sure everybody has all this written down. Okay. All right, so we'll go back to our tub of M&Ms. Okay. Okay, and so effectively, you know, we start off with a question: Is the tub %15% red M&Ms? Okay. All right, and so Is the tub 15% red M&Ms or is it more? Okay, we'll say more than 15%. Okay, so we'll go and we take a random sample. Of 150 M&Ms. So random sample from the tub, okay? And we count 30 red pieces. Okay. And so the question is, does this provide evidence that the tub is over 15% red M&Ms? Okay. So, what do you guys think? Okay, so 30 out of 150, that's 20% red M&Ms, okay? And the question is, so my random sample ended up 20% red. Is that evidence that the tub is more than 15% red M&Ms, or could the tub actually be 15% red, and just because of random sampling, I happen to get a few extra red M&Ms? What do you guys think? So you think evidence that the tub is over 15% red? Nobody? Could be a result of random sampling? Okay, well, let's see, all right? Okay, well, first of all, our first step will be to figure out what our hypotheses should be. Okay, so step one is to establish the hypotheses. Okay, so you need your null and you need your alternative. Okay, and then over here I'm just going to kind of list off our data, the data that we have. So we've got n is equal to 150, x is 30, so our p hat is 0.2. Okay, so we'll make this a clicker question. And so as far as hypotheses go, your choices are, so let me just write a bunch of null and alternative hypotheses. Okay, let's see. What do I want? I'll have p equal to point. Okay, so go ahead and make your choice. Yes, question. Where did I get to 0.2? So that is, if we counted 30 red M&Ms out of 150, 0.2 is 30 divided by 150, x over n. 30 divided by 150 is going to be 0.2. Okay, so I'm gonna hit stop here. Looks like you guys got it. Hold on. Oh. Oh no. Okay, I don't know if I can do anything. I'm sorry. I'm sorry. All right. Okay, and the answer is this. Okay, we're gonna say P is equal to 15% and P is greater than 15%. And the key here is that, does this provide evidence that the tub is over 15%? Okay, so that's why we want the greater than for the alternative, and the question is whether it's 15%. We're not going to go with B because B is using 20%, which is the value that comes from our data. Okay, and this is a question about the population, and so we're not asking if our data supports 15% or not. Is 20% or not. Okay. So step 2 would be check the conditions. And just for the sake of time, I'll tell you that the conditions are met. Okay. And we'll alpha is not specified, so we will use alpha equal to 0.05. Okay, so let's do our calculations. Okay, so the first part will be getting our standard error. The standard error for this hypothesis test, and we will encounter more hypothesis tests, is P0 times 1 minus P0 over n inside the square root, where P0 is the value that shows up in our null hypothesis. Okay, so because our calculations are based on the assumption that the null hypothesis is true, so this is the value that we're going to use here. Okay? Notice that this is different from a confidence interval. In a confidence interval, we used p hat. Okay? Okay, so a common mistake that students make is using the wrong p in the standard error. Okay, so for confidence intervals, you use p hat, and then for hypothesis testing, you're using p0. So in our case, if I plug in these values, I've got 0.15 times 1 minus 0.15 divided by 150, and this turns out to be, what is it? 0.15 times 1 minus 0.15 divided by 150. Whoops. And I'm going to take the square root of that, and I get 0.02915. Okay. And now I will get my test statistic. So the test statistic is kind of our observed minus the expected divided by the standard error. So in our case, it's going to be z is equal to the value we observe. The reality is p hat. What we expect to see is p0, okay? And we're going to divide by our standard error. So the reality is when we counted up our M&Ms, we got 20% red M&Ms. If the null hypothesis were true, we would expect to get 15%. Okay, so is this difference significant? Well, we're going to divide by our standard error to help us decide. Okay, so I do 0.2 minus 0.15, and I'm going to divide by 0.02915, okay? And I get 1.71. 1.71 or 1. Something very close to 1.72, 1.71 and a half-ish. All right, so my z ends up being 1.71. This is my test statistic. So far, so good with everybody? Yeah, question.
Question about step 2, where it says two conditions.
Uh-huh. Yeah.
A equals 0.05.
Yeah.
On the previous slide, you wrote 0.5.
Did I write 0.5? That was a mistake. Wait, let me see. Okay. File contains functionality. What? Only with what are you talking about? Okay. I don't know what's going on. Okay. No, 0.05. Use alpha equal to 0.05. Okay. Okay. So far, so good with our test statistic being 1.71? Okay. Okay. So now we are going to get a p-value. Okay, so step 3c is use the test statistic to get a p-value. So use your test statistic to get a p-value. And so this is how the rules for getting a p-value, okay? And it all depends on how the alternative hypothesis is written. So if the alternative has a greater than sign, then the p-value is the area to the right of the test statistic, and I'm going to just abbreviate to TS, okay? So if the alternative has a greater than sign, it's the area to the right of the test statistic, okay? And if the alternative has a less than sign, then the p-value is the area to the left of the test statistic. Okay. I guess the rules will be, look this up in the Z table. And this applies to chapter 8, okay? In chapter 9, things change on us, okay? But we'll deal with that when we get there. Right now, for chapter 8, this is what it is. Okay, and then if the alternative has a not equal sign, and then the p-value is 2 times the tail area. Okay? And then as far as tail area goes, so tail area is to the right of positive test statistics, and the tail area is to the left of negative test statistics. Okay. So, I think that makes sense over here. If you have positive, it's to the right, and if it's negative, it's to the left. All right, so negative. Okay, so in our case, our test statistic was z equal to 1.71. Okay, positive 1.71. We want the area to the right of z equal to 1.71. Okay, so what is this area going to be? Oh, let me pull up a reference table. 1.71, 0.9564 is over here. So I have 1 minus that, 0.0436. Okay, so my p-value is equal to 0.0436. Okay. How's this? It's good? Got a few head nods here. But all right. Okay, and then so now we want to use this to make a conclusion. All right, so our p-value is 0.0436. Let's first I'm going to start off with just kind of putting this into the understanding, and then we'll just use the, and then after that we'll talk about the kind of the hard and fast rule. Okay. So our p-value is 0.0436. Okay. What is the definition of the p-value? I'll go ahead and write it out here. The p-value is the probability of observing our data or something more extreme if we assume the null hypothesis is true. Okay. So, our null hypothesis basically said that the proportion in the tub is 15%. Proportion red in the tub okay. So what our p-value of 0.0436 means says that okay, if the tub is 15% red, then a random sample, bless you, it says then a random sample of M&Ms could end up being 20% red or more. So it could end up being 20% red or more, basically just from random chance, because of the random sampling process, okay? But what we're saying is that the probability of that happening is only about 4%, 4.36%. Okay, and so now we are faced with a choice. We have to decide, and there's no way to know what the correct answer is without looking at the population. We have to decide, okay, maybe the population, the tub is 15% red, and I just happen to be in that 4% where we got a bunch of red M&Ms in my sample. Okay, that's one scenario. Okay, it's possible that I'm just in that 4% that got a bunch of red M&Ms. Okay, the other scenario is, you know what, the tub is actually over 15% red, and that's part of the reason why I got so many red M&Ms in my sample. Okay, and the truth is we don't know what's correct, but those are kind of the two scenarios, the two conclusions I can make from this. Okay, so I have two possible conclusions. Okay. My sample is okay, actually let me back up. I'm going to say I still believe the tub is 15% red. I still believe the tub is 15% red, and my sample was just one of those. My sample is in the 4.36%, is in the 4.36% that happened to get a bunch of red M&Ms. Okay, I will not, you know, we will not reject the notion that the tub is 15% red. Okay, we will not. Okay, so that's one possible conclusion. Okay, and then the other possible conclusion is I don't think my sample was one of those weird oddities. Okay, I do not believe my sample is you know, in the 4.3 is in the 4% basically. Okay, instead, you know, I conclude that part of the reason why I got so many red M&Ms is that the tub is actually more than 15% red. Okay, so we conclude that the tub is greater than 15% red. Okay, so I'll let you guys get that all written down. So these are two possible conclusions, and I hope they make sense as far as kind of the line of reasoning goes. Okay, so either our sample is a result of just random chance alone, or the tub has more than 15% red, and that's why we got so many red M&Ms. Okay, so I could have gotten a bunch of red M&Ms because of random sampling, or the tub is more than 15% red, and that explains the reason why I saw so many red M&Ms. Okay. Okay, and so we have a p-value of 0.0436. All right, and so I think it's good to think about what the p-value means and what conclusions we should make, okay? But if we have to make a decision, a lot of times we just compare our p-value to alpha and make our conclusion that way, okay? And so as far as, can I switch to a new sheet here? Okay. So, so our p-value is 0.0436. So to make our conclusions, a lot of times we just compare our p-value versus alpha. And if we are using alpha as 5%, our p-value ends up smaller than alpha. Okay? And when our p-value ends up smaller than alpha, we are effectively saying, I don't think this happened by random chance. Okay? Our p-value is small enough that we conclude that it didn't happen from random chance alone. Okay? Okay, and so we say our p-value is less than alpha. We reject the null hypothesis. And we conclude that we have evidence that the tub is over 15% red. Okay. And so this conclusion is contrary to a lot of how you guys felt in the beginning when I said, you know, I happened to get 20% red M&Ms in my sample of 150. You know, does that feel like it could have been a result of random chance, or is this evidence that it's more than 20%? And a lot of you said it was just a result of random chance. Something's going on over there. But, you know, it's good that calculators are designed to take a beating, right? Because your phone, if you didn't have it in like a case, and like I'm running like high risk mode here, it's like you drop them and they like explode, right? So okay. All right, so this is what we have, and so yeah, we rather than just going off of our gut feelings and saying, I think it could have happened by random chance, we can do the calculations, and if we have a significance level, we can draw a conclusion. Okay, but there is a catch to all of this. Okay, and this is going to be the reality of statistics, but also your entire lives, is that anytime you make a decision, unless you know everything in the world, which is never, right? Anytime you make a decision, it could be the wrong decision, right? Anytime, and you cannot live your life paralyzed by fear that you're going to make the wrong decision. But anytime you make a decision, it could be the wrong decision, okay? And so when we look at this, and if we choose alpha to be 5%, we are effectively saying I am willing to be wrong 5% of the time. Okay, and so this is what I mean by this. Okay, we have something called a type 1 error. Okay, now when statistics was first being explored and people came up with names for these errors, they couldn't be more creative, and so they came up with type 1 error and type 2 error. Okay, and these are the types of errors you can make. As time went on, we kind of gave these better names. So we have so type 1 error is also often known as a false positive. Okay, and the type 1 error is our conclusion is to reject the null hypothesis. Okay, but in reality, the null hypothesis is true. So it shouldn't be rejected. Okay? And we got a p-value of 0.0436. We were using an alpha of 5%. So effectively, anytime our p-value ends up less than alpha, we're going to reject the null hypothesis. Okay? But when I get a p-value of like 0.0436, that's effectively saying that my data could be a result of random chance 4% of the time, effectively. Okay? So I'm saying, well, 4% is small enough for me to say I don't think I'm making a type 1 I'm making this error, but I could actually be making this error. Okay? So our significance level alpha is equal to the probability of a type 1 error. Okay, so let's just think about it. So if alpha is equal to 0.05, okay, then our p-value will end up being 0.05 or less 5% of the time. 5%, I'm going to write 5% of the time from random chance alone. Okay, and so that means 5% of the time the null hypothesis could be correct, but we just happen to get a weird sample, okay? That leads us to reject the null hypothesis. Okay, so that means even if the null hypothesis is true, ,5% of the time, a random sample will be quote-unquote weird enough to lead us to the wrong conclusion. Okay? And so even though we made the wrong conclusion, I want to emphasize that it's not that we've done something wrong. Okay? It's just that we are making conclusions based on a random sample. Okay? And the central limit theorem, we're counting on the fact that most of this time, random samples will be pretty close to what the actual population looks like. But because it's random, every now and then you just happen to get a random sample that is quote-unquote weird that leads you to the wrong conclusion. You didn't necessarily do something wrong, it's just that happens, okay? So this is type 1 error. This is our significance level alpha is the probability of a type 1 error, okay? On the other hand, we have a type 2 error, which we can call a false negative. Okay, and this is our conclusion is not to reject the null hypothesis, okay? But the truth is the null hypothesis is false, okay, and should be rejected, okay? We assign a letter to this, beta. Beta would be the probability of a type 2 error, okay? So as far as, so if you need help remembering, just, you know, alpha is like the letter A. alpha is the first letter of the Greek alphabet, so type 1 error is alpha. Beta is the second letter of the Greek alphabet, so type 2 error, okay? Actually, that's where we get the word alphabet from. Alpha and beta just stuck together. Yeah. Whoa, okay. All right. And okay, so we'll end with just a couple clicker questions. We'll create our grid of possibility, okay? Okay, so this is reality, and this will be over here. We've got our conclusions based on our data. Okay, so the reality could be null hypothesis is true and null hypothesis is false. And over here we have reject the null, and the alternative will be do not reject the null. I mean, not alternative, the other option is do not reject the null, okay? Okay, so you have, these will be your answer choices, okay, A, B, C, or D. And I'm going to ask, question 1 will be, which box represents type 1 error? Okay, so this will be your first question. Which box represents type 1 error? A, B, C, or D? Okay, so get your clicks in, and then the next question. So don't answer this yet until I stop this question. Okay, so okay, everybody got their clicks in. Which box represents type 1 error? I'm going to hit stop. Okay. Click, click, click. Okay, and then the next question will be, which box represents type 2 error? Okay. Okay, so get your clicks in. You can talk to your neighbor. Okay, so click, 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 click. Just a few more seconds here. Okay, and I'll fill in the fill this in. Okay, so box A was type 1 error, and then box D was type 2 error. And then, so what's B and C? These are the correct conclusions. So B is a correct conclusion, and over here we also have the correct conclusion. Okay, looks like most of you guys got that. Whoops. Okay, great. Okay, we'll see you guys on Friday.